I just want to introduce Professor Lixia Zhang from UCLA, who is our first session chair. And I just wanted to note that she is a recent recipient of the SIGCOMM Award at this year's SIGCOMM. So Lixia, I'll turn it over to you.
Thank you, Ken. Welcome to the first session of this second day of ICN. So our session will have three speakers. The first one will be the, forgive me if I don't pronounce your name right, there's Muktadir Chowdhury, who's a graduate student in the computer science department of the University of Memphis. And he's been actively involved in the named data networking project with a focus on the routing and the forwarding in wireless networks. Today, his paper title is Leveraging Content Connectivity and the Location Awareness for Adaptive Forwarding in NDN-based Mobile Ad Hoc Networks. So please start.
Hi, everyone. My name is Muktadir Chowdhury. I'm a PhD student at University of Memphis. In this talk, I'll be presenting my paper titled Leveraging Content Connectivity and Location Awareness for Adaptive Forwarding in NDN-based Mobile Ad Hoc Network. These days, wireless networks are everywhere, and mobile ad hoc network is a specialized wireless network which lacks infrastructure, and each node acts as a forwarder or router. They are very useful in many cases, for example, in vehicle-to-vehicle communication, military missions, or emergency response. For example, in vehicle-to-vehicle communication, data sharing enables vehicle to acquire information that is not in the range of the sensor, and it can help the vehicle avoid collision and know the road information and change the route accordingly. NDN has several unique advantages over TCP/IP for wireless mobile communication. For one, it has name-based forwarding, which means that the forwarder does not have to know the destination IP address of the packet. It can just look at the name of the interest and it can forward based on that name, and the data packet will follow the path that the interest took. And it also has pervasive caching and network layer security. In this talk, so in this work, we developed a forwarding strategy for NDN-based MANET that can make a smart forwarding decision with minimal or no routing information. First, have a look at what has been done so far in this area. There has been quite a few related work in NDN, but these are the ones that are most related to our work. Although many of these works are specialized for vehicle ad hoc network, but they can be applied to mobile ad hoc network as well. The first one is VANET via named data networking, or VNDN. So here, the forwarding decision is made based on the distance from the consumer. So the further a node is from the consumer, it will wait less time before forwarding. And another one is Navigo. Navigo's forwarding decision is based on the location of the data. So a node closer to the data location will be selected for forwarding. VNDN and Navigo, as you can see, that both are geolocation based routing. So they have the limitation that all geolocation based forwarding or routing has. So that is, they need to resort to broadcast whenever the location information is not available. There is another forwarding strategy which is very related to our work, is that is called Strive. In this scheme, they have a score for each node. The score is called the centrality score. Centrality score is the interest satisfaction rate of a node, which is a measure of the connectivity of a node. Nodes share their centrality score, and when forwarding, choose the next hop based on the centrality score. Since the network topology in MANET is always changing, Strive frequently needs to update the table when where it stores the neighbor's score. And another limitation of Strive is the calculated score applies to all the prefixes of a node. So it does not take advantage of the hierarchical data naming of NDN. In this work, we propose a forwarding strategy called CCLF for Manet environment. It is a tableless timer-based forwarding where each node takes forwarding decision independently. CCLF does not solely dependent on the geolocation, but it leverages geolocation in forwarding whenever it is available. And similar to Strive, it also uses centrality score, but it calculates centrality score per prefix while forwarding. Since the forwarding strategy is utilizing the broadcast nature of the wireless medium, CCLF employs node density aware packet separation mechanism to encounter broadcast storm. Here is a high level and simplified overview of how CCLF work. So this is our consumer, this is the producer, and these are the intermediate node. The consumer send out interest, the blue line denotes the interest, and here is the interest count and data count and centrality score and the location information. So 0 means currently these are unknown. So once the node receives the interest, they are going to calculate a timer. Since they do not have any information, they're gonna pick a random time to forward the packet. So let's say that node 1's timer expires first and it forwards the interest, but it got lost because there is no neighbor in its range. And the node 2 forwards the interest, and luckily it has some neighbors around its range, 5 and 3. Both will receive the interest, and 3 will, and both will calculate the timer based on their respective score. So as you can see that 3 has some information about the centrality score and the location score, but 5 do not have any information. So since 5 do not have any information, its timer is going to be higher than 3's. So 3 is going to send out the interest first, and which is going to reach 5 as well because 5 is in 3's range. So 5 is going to cancel the forwarding of its interest, and that interest is also going to reach 4 as well. And then the 4 will also calculate the forwarding time based on its centrality score and the location. And then after the timer expires, it's going to send out the interest to P. So the P is now going to send out the data packet. The orange line denotes the path the data packet is going to take. So before forwarding the data packet, the P is going to attach 2 pieces of information to the data packet. One is the location, data location, and another is the prefix under which it is serving the data. So as the data packet is will traverse its way back to the consumer, all the intermediate node will update their centrality score and the location information according to the information in the data packet. So as you can see that all the node updated their information of the centrality score and also the location score for this prefix. To store the per prefix location and centrality score, CCLF uses the tree structure. We call this CL tree. Each node in the CL tree has the name prefix and its corresponding score and location. The score represents how successful a node has been in getting data under a prefix. Each node in the CL tree calculates the centrality score of name prefix based on the percentage of satisfied interest for the name prefix and its descendant. When forwarding, CCLF don't use the absolute value of the score, rather it periodically updates the smooth score and use that value. We saw in the example that when a node receives an interest, it will wait for some time before forwarding. The timer is calculated based on the centrality score and the location score of the prefix. And this is how we are calculating the location score. The equation makes sure that the closer you were to the destination, the shorter your waiting time will be. So this is the distance from the node, from this node, from the data location, and this is the distance from previous node to the data location. So in this example, these are the 2 nodes, N1 and N2, and both got the interest from the previous node P, and this is the data location D. So here in this case, you can see that the N1 has higher location score because it is closer to the data location. After calculating the location score, each node calculates its weight based on the centrality score and the location score. CCLF uses smooth centrality score of the longest matched prefix in CL3. If a node has high centrality score, then for a prefix, it means it has route to the producer which is serving under the prefix, so its weight will be higher. If the location information is not available, weight will be calculated using only the centrality score. Then the forwarding delay timer is calculated by using this weight of the node. Higher the weight, lower the waiting time. Here, T is an upper bound on the small t. The forwarding timer is set to a random value uniformly distributed between 0.5 t and 1.5 t. So at the beginning, when a node does not have any information, the location does not have any location information or centrality score, the W will be 0. So then the small t will assume the value of the big T. After calculating the timer, CCLF schedules the forwarding of the packet based on the timer. But if it receives the same interest before the expiration of the timer, it takes decision whether to cancel the forwarding of a scheduled packet or not. The decision is made based on the suppression probability, which is proportional to the number of neighbors of a node. Higher the number of neighbor, the higher the probability of suppression. In the so here the F2 will have higher probability to cancel forwarding and suppress the received packet because it has more neighbors. We have run experiment to find a suitable value for K in suburban and urban environment. We are also using the same packet suppression mechanism to for data packet as well. To enhance the reliability of packet forwarding in mobile ad hoc network, we introduced ad hoc link adaptation layer. It sits between NDN layer and data link layer. It utilizes the beacon of the data link layer to keep track of the neighbors in the transmission range. In MANET, there can be times when there is no neighbor around a node. In that case, it is a waste of resources to send the packet. If ad hoc link adaptation layer detects no neighbor, it will queue the outgoing packets. And once it encounters the node, it is going to send out all the packet from the queue. In addition to that, ad hoc link adaptation layer is also responsible for getting the location information from GPS and attach the location header to the outgoing packet. We added a location header which has two optional fields, previous node's location and data location. Interest can carry previous location and data location. In the destination, in the data packet, destination location and the prefix announcement header is used. And each node attaches its own location in the previous location field before forwarding an interest. The CL tree is populated by the prefix announcement and the data location field in the data packet. This is how the CCLF addresses existing schemes limitation. Compared to the topology-based proactive scheme, CCLF has lower protocol overhead because it does not have any routing messages. It also incurs lower delay than topology-based reactive schemes. Because CCLF uses name prefix-based connectivity code to avoid initial learning delay. And comparing to the geolocation-based scheme, CCLF has lower protocol overhead because it uses connectivity code to get around local optimum and flooding. We have implemented forwarding strategy in NDN-CXX, library, and NFD. So we added NDN-LP headers in the NDN-CXX and the forwarding strategy in NFD, and the ad hoc link adaptation layer is implemented in the transport service. We have done simulation using NDN-SIM and generated map and traffic trace using Sumo. And to evaluate our forwarding strategy, we use this matrix. So interest satisfaction ratio is the ratio of the data packet the interest got back and the interest that was sent by the consumer, and the data fetching delay is the delay incurred by a data packet when before it got back to the consumer, and message overhead is the total number of interest packet and data packet in the network during the time of the experiment. We use a vehicular ad hoc network as a case study to evaluate the performance of CCLF. VANET is a specialized mobile ad hoc network where nodes move with high velocity. Many vehicular ad hoc network applications are time sensitive, but vehicular connectivity is typically short-lived, which makes it difficult to fetch data on time. So running the experiment in this vehicular ad hoc network environment gives us important insight into the CCLF's performance. So these are the communication parameter setting, and these are the traffic parameter setting. We created a 3x3 grid road topology. The area of the grid is 300 by 300 square meter, and the speed of the vehicle is between 7 to 13 meters per second. Before running the experiment, we wanted to see how the number of neighbors varies for various traffic conditions in urban and suburban setting. The grid road topology simulates the urban environment, and two-lane road topology mimics the suburban setting. In the table, we can see the results. Then we also run experiment to pick a suitable value for K in grid topology. The figure shows the effect of setting the suppression constant to be 0.04, 0.08, and 0.112 on the performance of CCLF in grid road network. Based on the above result, we decided to use K equals to 0.12 for the remaining experiment, as it gives a satisfaction ratio as good as that of flooding and reasonable delay range, but has the lowest protocol overhead among all the cases. These figures are showing the performance comparison among CCLF, VNDN, Navigo, and flooding when geolocation information is available. We use the grid road network in this set of experiment. There is one consumer and one producer. Consumer is sending 1 interest per second. We can see that CCLF's satisfaction ratio is higher than VNDN and Navigo, and almost same as flooding. Moreover, CCLF has much less protocol overhead than the others. And as for the delay, its median delay is almost same as the others, and it has lower 95th percentile delay. Here we ran experiment in the same setting, but compared CCLF with a centrality score-based strategy called STRIV. Here we can see that CCLF has much higher satisfaction ratio than STRIV. However, STRIV has lower protocol overhead and delay. It is attributed to STRIV's uniquest nature mostly, but we have also run experiment for multiple consumer and multiple producer where CCLF showed much better performance. Please refer to the paper for detailed discussion on the results. To conclude, as you saw from the result, that CCLF incurs much lower protocol overhead due to its less flooding, density-aware packet separation, and packet queuing at ad hoc link adaptation layer. CCLF incurs lower delay because name prefix-based connectivity helps to avoid initial learning delay and to find better connected path to the producer. Our future works include study different ways to calculate forwarding timer and suppression probability, and offer guidelines on setting CCLF parameter. Thank you.
Thanks for the presentation. I think there are a number of questions on the Slack. Let me just pick a few. One asked about the prefix granularity. I see that you already answered to say this based on the longest prefix match.
Right.
However, given that there's no routing announcement per se, what you learn from the data is the longest prefix. So then the further interest comes, you have no other choice other than just match the exact data name. Did I get it right?
Okay, so your question is that, so since we do not have any routing announcement, so whatever the producer tells you, so that is your, your interest has to match that exact prefix. Is that your answer, question?
That's the question, yes.
Yeah, that is correct. Yeah, so we are relying on the prefix announcement from the producer.
And then there's not so much of the longest match per se. There's a next question, I think it's a shared one by a few people. It's about how you decide the location. I think that didn't get explained clearly in the presentation. Maybe you can give a further illustration here.
Okay. Yeah. So yeah, we are. The producer is going to attach its own location to the returning data packet. So yeah, it is like right now we're using like longitude and latitude, and each node, like before it forwards the interest, it is going to put its own location information in the previous hop field. So this is how we are calculating. So when a node receives an interest, it can calculate the location score from the like previous hop field and the data location field.
Okay, thank you. Let me ask another question that hasn't shown up on the Slack yet. That is, throughout the whole presentation, I did not see mentioning about security. And therefore, there's a question of either some malicious cars gonna inject the interest to overload the system, or otherwise, if there are other cars that respond to the interest with the false data, how would those situations get mitigated?
Okay, yeah. So yeah, in our paper, so yeah, in this paper, we did not focus a lot on the security. We are mostly focusing on the forwarding part. But in our previous work, we focused on the security part, and there we proposed a trust model, how a data can be signed by vehicle and when a data is received by a vehicle, how it can verify the data. So according to that trust model. So in our paper, we briefly talked about it, that okay, we can use a similar trust schema for the vehicular application, and yeah, so and for different other managed application, we can use other like different kind of trust model specific to the application.
I think for the end, for the consumers, you can definitely have trust models to validate the results, whatever your trust model is. Although that itself, I think it's remain as a research topic. That is, with the cars, how can you build the trust model that still have a strong privacy protection? But leave that for now. There's a question of the intermediate forwarding cars, where they forwarded the data. So therefore, next time, if they see the interest of matching prefix or matching name, they're gonna do the forwarding. So that, I think, expose a bigger challenge of how you can clear up the state is already in the system created by the false data.
Okay, so in this case, you are saying that if another vehicle announce some false prefix, right? Announce some false prefix, and that is going to be in the system, and other people are also going to be using that prefix for their forwarding.
Right, that's the issue.
Yeah. Right. Yeah. So yeah, in that case as well, like what I think can be done as a first line of defense is that we can sign the prefix announcement as well. So using that trust model, for example, and have the end party verify the prefix announcement itself, and they can verify it.
I didn't get clearly. You mean that the intermediate forwarder will do the verification?
Right. Yeah. So yeah, all of them is going to be so whoever is going to use the prefix announcement, all of them are going to verify it using that trust model. And once it is verified, once they know that okay, this is from a verified party, I trust this prefix announcement, then they are going to use it.
I think we're running close to the time limit, but let me just inject another comment here. It is actually a research question, that is whether you can assume the whole system share the same trust model. That has always been a outstanding issue, whether the end users would have the same trust model as everyone else. Keep that in mind. Let me read this last question I saw from the Slack. It says that the proposal use breadcrumb chunks to data package delivery, but you consider the high mobility in MyNet.
The proposal.
That is to say that you have the interest leaving out the breadcrumbs along the path for the data to come back. But in a highly dynamic VANET environment, is that assumption still valid?
Yeah, so we are using we are flooding the packet basically, right? So eventually it is going to reach the consumer. So that is what we are assuming here. We are relying on the broadcast medium of wireless.
The broadcast actually get pruned as you mentioned in your presentation. Some nodes didn't have forwarding information, so they drop it, and only most likely the interest is going to go along the direction of where the data has been seen previously. But I can help offer some input here. I think Giovanni Paul, I don't know whether he's here, he led a team doing this kind of simulations before, and we did that too. Actually, you won't believe cars move at a physical speed, and the packet moves at the speed of light. So therefore, yes, you can have very highly dynamic VANET that doesn't really destroy the breadcrumb left by the interest before the data comes back. So this has been validated, at least through the simulation with the real parameters.
Right.
Thank you very much for the presentation, and let's move the rest of the discussion to Slack. Then we go on to the second talk of the session. This one will be presented by Martine Landers, who's a PhD student in computer science at the Freie University Berlin. So she's a contributor to the RIOT operating system. That's for the support of constrained IoT devices, and maintains its networking architecture. So her primary research focus is on IoT communications and embedded programming together with information-centric networking. Her presentation topic is connecting the dots, selective fragment recovery in ICNLoWPAN. So let's get started.
Welcome and thanks for joining my talk. I'm Martine Landers, and together with my colleagues Cenk, Gündoğan, Thomas Schmidt and Matthias Wählisch, we worked on integrating the emerging IETF standardization around fragment forwarding and selective fragment recovery into ICNLoWPAN. ICNLoWPAN is the ICN adoption layer for low power and lossy networks currently proposed within the IRTF. First, I will talk about our motivation and give a short introduction on fragmentation within ICNLoWPAN. Then I will present you our proposal to address the problems we encountered in form of the so-called virtual reassembling endpoint. For the virtual reassembling endpoint, I will then provide you with our evaluation and compare it to established approaches within ICNLoWPAN. Last, I will conclude my talk and give you an outlook on our future work. So, the first question you might ask yourself is, why do we need fragmentation in ICNLoWPAN at all? Well, if we look at the classic internet, we encounter PDUs that usually provide us with more than enough space to carry all the information we need. When looking at the embedded IoT, however, we face PDUs of only a few hundred bytes. To be able to communicate with a wider internet regardless, ICNLoWPAN introduces both header compression and fragmentation, the latter of which will be the focus of this talk. However, the rules of fragmentation and reassembly are different in ICNLoWPAN, as you might know it from other protocols such as IP fragmentation. Since the forwarding information is only carried in the first fragment in ICNLoWPAN to save space, a decision needs to be made for how to forward fragments. The classic and naive approach is hopwise reassembly. Here, when the first fragment arrived, it is added to the reassembly buffer that is then filled up with subsequent incoming fragments which are identified by the link-specific datagram tag until the full datagram is reassembled. When the network layer then comes to the conclusion to forward the packet, it is refragmented again. However, this approach wastes a lot of memory, as we need to allocate enough space to hold every datagram that is incoming. Given that on the type of nodes we are working with in the IoT we only have a few kilobytes of memory, this can lead to a forwarding bottleneck. Alternatively, we can forward fragments directly by utilizing the so-called virtual reassembly buffer to associate the datagram tag with the forwarding information. Here, when the first fragment arrives, we look up the forwarding information in the network layer and create a virtual reassembly buffer entry based on that. This way, we don't have to store the whole datagram for forwarding, saving resources. The incoming fragments are then forwarded directly without any reassembly. Compared to hopwise reassembly, this can be implemented with only a few bytes of memory in RAM. In both cases, however, we face the problem that if only one fragment gets lost, the whole datagram is lost and might need to be retransmitted by an upper layer. For this, selective fragment recovery was introduced, where for a collected number of received fragments, the window size, a cumulative acknowledgement message is sent by the reassembling endpoint. The accumulation of acknowledged fragments is achieved by using sequence numbers in the fragments and a bit mask in the ACK where each bit represents a completed fragment with a sequence number equivalent to the position of the bit. In the given example, the fragments with sequence numbers 1 and 2 are acknowledged by the first 2 bits in the ACK being set. Using a reverse lookup in the virtual reassembly buffer, this acknowledgement can be forwarded by intermediate nodes to the fragmenting endpoint. When the acknowledgement signifies that a fragment is lost, the fragmenting endpoint has a chance to resend only the lost fragment, which is then forwarded and the acknowledgement returned as before. Another ICN-specific problem when forwarding fragments is that while with hopwise reassembly the forwarder sees the completed datagram at some point in the process and thus enables ICN to add the completed content chunk to its content store, direct fragment forwarding, however, does not allow for that. ICN uses content chunks, but since they are fragmented datagrams, we never see the full chunk. In turn, we are not able to cache forwarded content chunks when directly forwarding fragments. But is there maybe a way to have the advantages of both? When we look at the requirements for that, we of course want to fulfill the two identified advantages first. So we want to make the full content chunk available to an ICN forwarder, even if fragment forwarding is used, and be as frugal with memory as direct fragment forwarding is. As such, should our implementation mostly reuse existing data structures and only slightly extend them. Additionally, it should be compliant with the given standards, meaning that our proposal should be transparent to the network. The cached fragmented content chunk should behave like any other content chunk, but should be unable to poison the network with incomplete data. In our proposal, the virtual reassembling endpoint extension, short VRAP extension, the content chunk is reassembled tentatively en route to in the content store. Such a tentative content store entry, however, is not served to incoming interest as per our requirements. So only if the datagram was fully acknowledged, the content store is made available to incoming interests. Another benefit with this approach is that if the acknowledgement is indicating a loss, this fragment can be restored directly from the content store and act according to the fragmenting endpoint if the fragment information is retained. To evaluate our proposed virtual reassembly buffer extension, we compared 3 approaches to fragment forwarding. Classic hopwise reassembly, which in our results we abbreviate as HWR. Classic selective fragment recovery without the virtual reassembling endpoint extension, short SFR without VRAP. And finally, selective fragment recovery with our proposed extension, short SFR with VRAP. We picked 2 topologies based on previous experiences. A daisy chain topology that consists of 7 hops between the consumer C and producer P to benefit caching behavior, and a Y topology that consists of 1 consumer C and 2 producers P1 and P2, with the consumer and producer separated by 2 hops F1 and F2. Note that F2, the forwarder closest to the producers, forms the previously discussed bottleneck. For the sake of time, I'd like to ask you to look up further setup and configuration parameters in our paper, please. First, let's have a look at the time to completion, or TTC for short. You can see 2 CDF plots, one for each topology, with a time to completion in seconds on the x-axis and the CDF on the y-axis. The datasets for HWR are represented as an orange line, for SFR without VRAP as a blue line, and for SFR with VRAP as a green line. Note that for the daisy chain topology we added a zoom in, as the completion rate never becomes greater than 3%. For the Y topology, we did not see any successful completed requests with SFR without VRAP, which is why we do not see any CDF for it in the right plot. But also, in the daisy chain topology, we see only less than 1% of the requests completed. So, selective fragment recovery without the virtual reassembling endpoint extension performs completion-wise bad in both topologies. For the daisy chain topology, hopwise reassembly performs slightly better than selective fragment recovery with the virtual reassembling endpoint extension, but comparable. In the Y topology, however, SFR with VRAP performs much better, twice as good as hopwise reassembly. Since we pre-configured the window size for our experiment statically to 1, HWR always has a slightly shorter TTC than both SFR variants, as SFR requires an ACK exchange in addition. We picked this window size to reduce noise, since the minimal congestion control mechanism proposed in the draft always ended up at 1 in our setup anyways. Looking at the content store hits, so when an interest is served by the cache rather than the producer application, we only compared the behavior within the daisy chain topology. The figure you can see plots the nodes within the network, consumer C and forwarders F, 1, 2, etc., marked on the x-axis. F6 is closest to the producer, F1 is closest to the consumer. The number of content store hits at each of the nodes is on the y-axis. Hopwise reassembly is seen in orange bars. Selective fragment recovery without the virtual reassembling endpoint extension in blue bars, and selective fragment recovery with the VRAP extension in green. In general, both SFR variants experience less cache hits closer to the consumer, which leads to an increased content store access at the producer. As the SFR implementation used in our experiments falls back to hopwise reassembly when the reassembly buffer is full, we also contrasted the cache hits with the number of events when the VRB is full in a scatter plot to better understand the impact of that behavior. In this scatter plot, we see 3 clusters. The one on the left represents all results for SFR with VRAP, which mostly bunch up on the y-axis. The 2 on the right represent the SFR without VRAP dataset for forwarders 5 and 6, so the ones closest to the producers. From these plots, we can see that the cache hits with SFR without VREP solely come from the SFR fallback, while for SFR with VREP, they come from the virtual reassembling endpoint extension. In summary, our evaluation shows that the proposed virtual reassembling endpoint extension for selective fragment recovery fulfills the requirements we set for it. It saves memory by reusing existing data structure and additionally is serving the full content chunk to ICN forwarders. It also shows that using SFR without the VREP extension yields the worst results in any case. For topologies with many hops without intersection points, hopwise reassembly has a slight advantage over selective fragment recovery with the VREP extension, though negligible. However, when there are intersection points in the network, those will form a bottleneck in the reassembly buffer of hopwise reassembly. Here we get significantly better results for SFR with the VREP extension over hopwise reassembly. For our next steps, we plan to analyze the impact of the virtual reassembling endpoint extension with more complex MAC layers, such as IEEE 802.15.4, also known as TISH, different congestion control mechanisms with SFR, and different ICN caching strategies. Thank you for your attention. If you have questions, please ask them. I can give you, however, already an answer I'm sure many of you are burning to have answered. Is our research reproducible? And I can say yes. You can find all the code of our experiments both on GitHub and the ACM digital library.
Thanks for the presentation. This one, I think, went really smoothly as far as the video quality is concerned from my endpoints. I think I was a part of the discussion on the Slack regarding the related works previously. Do anyone else have other questions to raise? So I think the others already answered the comments on the Slack. But other than that, we haven't seen other questions. I'll give 10 seconds to see whether anything else shows up on the Slack.
Okay, it's just a comment on my previous answer. I guess I can give a comment on that. We also try to be compatible with ICNLoWPAN and CICLoWPAN. So all of the NDN proposals, at least that the ones we looked at, weren't seem to be lacking on that or didn't consider that. And so yeah, that's the main reason why we that's the main motivation behind the talk, that we wanted to extend ICNLoWPAN to be compatible with fragment forwarding.
Mm-hmm. I agree that I think the compatibility with the CICLoWPAN definitely is a unique feature of this work. Yeah. I think the earlier NDN technical report merely argued and pointed out that the packets must be reassembled hop by hop. That's actually independent from, actually that's the length of the name is one of the reasons that you must do hop by hop reassembly, so that you actually know where to further forward if you need to.
Yeah, we mentioned in our paper that is, sorry?
Okay.
We mentioned that in our paper that if the name is fragmented over the datagram, then of course you can't do direct fragment forwarding, but you have to do hopwise reassembly then.
So I think again, Junxiao offered you some further comments. So we can continue that conversation on the Slack. For now, let's move on to the third and the last talk of this session. That will be presented by Cenk. if I pronounce his name right this time. So the title, so he is a PhD student at this Hamburg University of Applied Sciences. He works on the several aspects that allow for information-centric IoT development in the low power and the lossy networks. Currently, he and his colleagues focus on bringing the NDN principles like stateful forwarding and hop-wise caching to pre-existing IoT infrastructure that the IETF has been developing a full suite for the standards. So let's welcome Cenk. The title for the paper is Towards a RESTful Information-Centric Web of Things, a deeper look at the data orientation in CoAP. Yeah, let's get started.
Thank you for joining this talk. I'm Cenk Gündoğan, and together with my colleagues Christian, Thomas, and Matthias, we explore a RESTful information-centric web of things. In our paper, we progressively add information-centric principles to a common IP-based IoT deployment and investigate whether the benefits of stateful forwarding, caching, content object security, and location independence of data show similar performance results as they do for CCNX and NDN. The common Web of Things deployment consists of constrained IoT devices, a gateway with uplink connectivity, and cloud services. The IETF protocol suite uses the constrained application protocol CoAP on top of UDP to provide an end-to-end connectivity between IoT devices and the cloud. And end-to-end security is provided by DTLS, which is the Datagram Transport Layer Security. The CoAP proxy functionality allows for protocol conversions, for example from CoAP over DTLS to HTTP over TLS, and integrates a response cache to reduce the number of hop traversals for previously requested content. This has the issue of terminating security channels at the gateway itself, and the gateway now has to be included in the trust relationship between the IoT device and the cloud. OSCORE is the IETF solution to provide content object security for CoAP and enables an end-to-end security that goes beyond untrusted proxy gateways. We observe that standard CoAP features can enable information-centric properties, such as stateful proxying or forwarding, content caching, and content object security. In our opinion, having an information-centric Web of Things allows for an early deployment chance of many of the ICN principles and benefits in pre-existing IP-based IoT infrastructure. We therefore pursue two research questions in our paper. First, can we build a RESTful Web of Things with CoAP that also displays characteristics of an information-centric network? And second, would such a deployment yield similar network performance results as a pure ICN deployment in the IoT? In the remainder of this talk, I will focus on our approach of constructing an information-centric Web of Things deployment using standard CoAP features. I will then present our analysis that compares different integration levels of the construction phase to pure CCNX or NDN deployment. And then I conclude and draw the next steps for our future work. Let's first look at the protocol operation of a plain CoAP deployment. Next to other methods, it supports the request-response model using a GET method. The client sends a request and the server returns a response, which either contains an error code or the requested content. CoAP also allows to piggyback the acknowledgement for the reception of the request. CoAP supports optional reliability for messages. This means client and server endpoints configure acknowledgement timers, and if no acknowledgements are received during this time, then retransmissions are sent from the endpoints. We compare this plain CoAP setup against this list of selected ICN principles. The forwarding is handled on the IP layer and is therefore stateless. There is no caching on the intermediate hops involved. The data exists on the endpoints and is addressed using the server's IP port tuple and the CoAP resource name. And at best, this setup uses DTLS to secure the transport between endpoints, but not the content itself. We now construct a CoAP deployment that displays similar characteristics as a pure NDN deployment. First, we loosen CoAP's end-to-end principle by deploying a CoAP proxy on each hop along a request path. With this method, each request is addressed to the next hop proxy, and this proxy generates in turn a new request for its next hop. And this process repeats until the request reaches the origin server. Returning responses traverse the exact same request path from proxy to proxy towards the initial client node. This forwarding behaves very similar to the forwarding in CCNX and NDN with their pending interest table. Further, each proxy hop configures acknowledgement timers, so that each proxy hop triggers retransmissions on message timeout. And CoAP proxies also implement a response caching feature very similar to the CCNX and NDN. From previous studies, we already know that a hopwise caching can greatly improve the reliability by shortening the request path and reducing the amount of unwanted retransmissions. Since requests are addressed directly to the next hop proxy node, IP addresses can be linked local and do not point to the original content servers anymore. The forwarding is now handled by the CoAP proxy, and forwarding decisions are made using the CoAP resource name. In our evaluations, we will compare the two depicted setups, the first without caching and the second with caching, to a pure NDN deployment. We call the first setup CoAP minimum proxy and the second setup CoAP proxy. Now let's have a look at the security principle. The IETF provides OSCORE, the Object Security for Constrained RESTful Environments protocol, which is a proposed standard since July 2019. OSCORE itself builds on top of COSI, the CBOR object signing and encryption protocol, and inherits the authenticated encryption with associated data method. OSCORE provides confidentiality, integrity, a strong request-response binding, and non-replayability of previous messages. A potential problem with a strong message binding is that it prevents cache hits from subsequent requests, even if they originate from the same source. And this is a topic that we are currently trying to address in our ongoing studies. For this paper, we consider response caches to be retransmission caches in order to recover lost messages of the same transaction from hop to hop. We now have a deployment option at hand that uses standard CoAP features and displays information-centric properties. In our evaluations, we analyze different metrics that are relevant for operations in constrained IoT deployments. We perform all our experiments on real hardware using the IoT Lab testbed, which provides deployments on several sites across France. We use the M3 node as our hardware platform. It features an ARM Cortex-based architecture with 64 KB RAM, 502 KB ROM, and includes the 2.4 GHz-based 15.4 radio transceiver with basic MAC layer features. The IoT devices run the RIOT operating system with external packages, libOSCORE and CCNLite, and we deploy our experiments on the depicted multi-hop topology. It includes 12 producer nodes and 11 forwarder nodes, and they statically arrange on a destination-oriented directed acyclic graph. For our experiments, we consider a converged-cast scenario. This means the gateway periodically requests a 2x temperature reading from the IoT devices. The RIOT network stack architecture follows a recursive design that easily allows for stacking and exchanging protocol layers. In our configuration, we use the GNRC network stack, which provides 6LoWPAN, IPv6, UDP, and CoAP. We extend CoAP with the CoAP proxy and caching functionality, and then we integrate the external libOSCORE package. CCNLite provides NDN and directly communicates with the MAC layer and the application. In our first analysis, we look at the packet structures for each message type of all considered deployments. We have to keep in mind that we are using a radio technology that is optimized for long battery lifetimes. This means we have a low bandwidth and higher latencies. Another constraint is a maximum frame size, which is limited to 127 bytes. Any frame that surpasses this limit has to be fragmented, for example with the 6LoWPAN adaptation layer. Any additional packet overhead generally increases the packet airtime and makes transmissions more and more prone to packet loss. For comparability reasons, we configure each deployment with the same security algorithms, which is AES 128 in CCM mode and 8 bytes for the message authentication code. We first consider the packet sizes for CoAP without any security measures and observe a MAC header size of 23 bytes. IPv6 with 6LoWPAN uses 35 bytes, the UDP header consumes 6 bytes, and the actual CoAP request message uses 18 bytes. For the response, we observe similar sizes, but the CoAP part reduces from 18 bytes down to 9 bytes. This reduction for response messages comes from an optimization of CoAP. Responses do not include the resource endpoint URI that is in the request. Instead, they use a 2-byte token to match the corresponding request. CoAP with OSCore increases the request message by 14 bytes, including the structural overhead for OSCore and the message authentication tag for an ensured integrity. In contrast, the response message increases only by 11 bytes due to an optimization of OSCore to reuse the same nonce for its AES operation in requests and in responses. The nonce is therefore omitted from the response message and implied by the requester on reception. Our proxy configuration uses a proxy URI string option within the CoAP header of the request to designate the proxy endpoint. This option is only included in the requests for intermediate hops and increases the requests by roughly 40 bytes. The request on the last hop removes the proxy URI option and therefore yields the message size of a typical CoAP message. Interestingly, since we are using linked local IPv6 addresses for proxied requests and responses, 6LoWPAN is able to remove the source and destination IP address completely from the message. The linked local IP address is then derived from the MAC address. The secured variant behaves very equivalently and additionally includes the message overhead of OSCore. We now move to the NDN setup. Because NDN replaces the network layer, we do not see a packet overhead related to 6LoWPAN or UDP. The MAC header counts 23 bytes like the previous CoAP deployments. The interest and data packets show smaller packet sizes compared to the unsecured CoAP case, and interestingly, the response in NDN is larger than the request. This is because NDN reflects the content name that is present in the interest message back in the response message. In the secured NDN setup, we add security measures to response messages and observe a message increase of 46 bytes. Our main takeaway from this dissection is that the stateful CoAP proxying actually can reduce header sizes for en route messages. In our next evaluation, we measure the completion time for all content requests across all sensor nodes. This means how long it takes for a request to be satisfied with the response. We already know from our previous experiments with the 15.4 radio that we can expect completion times in the range of milliseconds. CoAP and NDN also use a retransmission mechanism, and we configured 5 retransmissions with a 2-second timeout between each of them. If a request is not satisfied within 10 seconds, it times out. We first consider the unsecured protocol variants. NDN is able to satisfy close to 60% of the requests in the sub-second range. Retransmissions were able to recover lost messages within 10 seconds, so that NDN ultimately shows a reliability of almost 100%. Next, we see the performance for our plain CoAP deployment. The first configuration is CoAP None, which is a CoAP deployment without any retransmissions. We observe for the setup that below 80% of requests are satisfied in the sub-second range, and the rest is unrecoverably lost. The CoAP Con setup is performing end-to-end retransmissions, which also reflects on the staircase pattern of the plot. This deployment recovers lost messages and increases the overall reliability to above 80%. The CoAP minimum proxy deployment is doing stateful forwarding and hopwise retransmissions as NDN, but does not deploy caches. We see that this setup generally performs worse than the plain CoAP deployment because of the added network stress due to unneeded request retransmissions that is happening on all hops. If we add the missing ability of doing hopwise content replication, then we see completion times that are very similar to the NDN deployment. This CoAP proxy deployment yields a reliability of close to 100%. With enabled security features, the results look generally a little bit worse because of inflated message sizes. NDN and both plain CoAP deployments show, however, similar results as before. The CoAP minimum proxy deployment without caching is not able to recover the increased amount of lost messages. Additionally, lost messages multiply the number of retransmissions greatly, which then again leads to more packet loss due to the increased retransmission load that applies in parallel to the periodic requests. Here again, adding the content cache functionality boosts the reliability up to the level of the NDN deployment. Our takeaway for this evaluation is that a CoAP deployment with similar information-centric properties yields a similar reliability as the pure NDN deployment. In our next evaluation, we take a deeper look at the actual link stress in the topology for each deployment during the course of the experiment. In the plots, the links are grouped and sorted by their distance to the gateway from left to right. For the NDN setup, we see an increased number of requests and responses for links that are closer to the gateway, which is expected due to the chosen tree topology. The number for requests is also higher than the number for responses, which is also unsurprising because of the request retransmissions. The plain CoAP deployment without the retransmission functionality shows an overall link stress that is much smaller. CoAP with end-to-end retransmissions displays much more link stress. Interestingly, the number of requests is much higher than for NDN, and the number of responses is lower. The CoAP minimum proxy setup with hopwise retransmissions and no caching shows the most overall link stress so far, which is consistent with our previous reliability analysis. The amount of request retransmissions increases greatly, while the number of successfully returning responses is unacceptably low. If we now add the caching ability to this deployment, then we see the same results as for our NDN setup. We show with this analysis that the combination of stable forwarding, hopwise retransmissions, and content caching on intermediate hops reduces the overall link stress in multi-hop topologies. In our last evaluation, we analyzed the nodal packet loss and cache utilization of the secure protocol variants for NDN and the CoAP proxy deployments. Each matrix is arranged like displayed in the legend in the bottom left corner. The producer nodes are numbered from 1 to 12 and placed from left to right on the x-axis of each matrix. The y-axis shows the request path from top to bottom like displayed in the topology tree in the top left corner. First, we look at the request loss for NDN and CoAP proxy and observe a comparable behavior. Request losses are more likely to happen on links that are situated closer to the gateway because they are used more extensively due to the tree structure and the converged cast traffic pattern. CoAP proxy shows up to 25% requests getting lost on the topmost row of the matrix, which represents the links that connect directly to the gateway node. NDN, on the other hand, displays slightly less request losses with up to 20%, which is expected because of smaller request packets. On the other hand, our NDN configuration yields larger data packets compared to CoAP proxy because of the signature and the full name that is mirrored back in the data packet. And this is reflected in the nodal loss rates. NDN shows slightly more response losses across the whole network. In our setup, cache hits appear for request retransmissions. Since we observe slightly more response losses for NDN, we naturally observe more cache hits for retransmitted requests in the NDN setup. We have seen in the earlier evaluations that both setups yield a really good reliability with a success rate of close to 95%. Nevertheless, we also observed in this evaluation that we actually experience request and response losses. And the intention of this analysis is to support our previous statement that cache hits successfully shorten request paths and recover response losses. We highlight 3 takeaways from our comparative performance study. First, we can build an information-centric web of things using CoAP standard features. Second, stateful forwarding and hopwise content replication by using CoAP proxies along a request path improves reliability for CoAP. And third, the presented CoAP proxy deployment provides an early deployment chance for ICN principles in existing IoT infrastructure. And this leads us to our future work. With this CoAP setup, we can see how well CCNX and NDN-based forwarding and caching strategies could be reused in CoAP. We also plan to look at the multicast capability of this setup. Thank you for listening. We support the recent ACM initiative to reproducibility. For this, our experimentation code and data are publicly available at this GitHub URL. All protocol implementations are part of the free and open source IoT operating system RIOT.
Thanks. That's really a great talk. One thing I really want to learn from that is that I think it's the best the video embedding into the presentation. I wish I knew how to do that. Because I'm going to start for teaching next quarter. I have to do recording as well. But that's a comment aside. There's a fair amount of discussions on the Slack. I think if I get it right, you have to multitasking. There's basically two types of comments. The very first one is regarding routing and forwarding that also relates to the reliability evaluation and the statement that made in the presentation. In the evaluation, it seems that it's a simple topology. The packet only has one way to go, so therefore this aspect wasn't either discussed or even described. How does one node knows where to do forwarding when you do the CoAP? Does it have a routing protocol or something to direct the packets where it goes?
Yeah, so thanks for the question. So actually the main goal was to show that we can deploy CoAP deployment displaying these features that we also have in NDN. For this, of course, we wanted to have a very simple topology first, of course, using static topology, which we also use for NDN, by the way. So they both have static routes in our examples. But in the end, I mean, since we do the routing based on URLs, so based on names in the end, I could imagine that we can have similar like routing mechanisms, and there are plenty of them for the NDN world. And I can imagine that we can also like move them to the CoAP deployments. I mean, since we are, I mean, it's equivalent. We have names, we route on names on the proxies. We could also have backup names, backup routes, which is also supported.
I think everyone who except Junxiao on the Slack conversation, you actually are co-host. You can speak out directly. We have another 10 minutes for discussion, so please feel free to jump into the Zoom discussion. That's probably more direct than I could capture your opinions on the Slack. But let me just respond to Cenk's reply. I think there is a basic difference. It's not so much whether IP and NDN can both run routing protocols. I think the question goes deeper than that. Because for IP, you actually got two different classes of identifiers. You do routing on the address. Then you have to do all these other things like caching and whatever on the data names. So that introduces additional mapping and complexity. I
agree completely. Mm-hmm. But I mean, the thing we are doing with the deployment is that we only forward to the next hop. So so we are using a link local IP address, and the routing itself happens on the proxy level, in the upper levels of the stack, then based on the service URL in CoAP.
The next question, I think, is related to the system complexity. As we all know, I think you know way better, perhaps, than others, given you spend the effort doing this level of research. That is, IETF CoAP actually evolved substantially over the years, adding pieces one after another, so that in terms of purely measuring the packet delivery performance, it gets into more or less what the ICN approaches can do. But in doing so, they added pieces. So there's a start with there's a DTLS, then object security. Then they have to consider caching, which is not part of the IP design to start with. So therefore, you think about a system which is an assembly of various pieces versus another system like ICN, where it's a coherent design. just name the secured data chunk. And I think if one does complexity analysis, there can be very interesting results. Myself, my personal bias, I just want to make one more statement, and I should let other people talk. In evaluation, somehow I feel that the younger generations were taught to only evaluate performance, the delays, the throughput, and they do not actually, the trend is not looking at other aspects of the system, which can be more important than the pure performance and the throughput delays. Delays other than speed of the light, all other delays can be adjusted, can be improved. But the system complexity doesn't really get better when the chips go faster or the link go higher speed. I'll just stop there, and I hope other people jump in, like Dirk, like Dave or Ran, and you people keep chatting on the Slack. Why don't you speak up here? We have another 5 minutes to spare.
Yeah, okay. So I really enjoyed the paper. So I think it was really interesting to see the comparison. But I generally agree to what Lixia said. It's possible to set up a CoAP OSCORE system with like in a very specific setting that maybe behaves on par with an say ICN NDN system. But I think you really have to consider the bigger picture. So what do you have to add to make it really feature comparable? And so dynamic routing, and what if the network has problems and is dynamic, and so on. The extra caching functionality. So just as a question, would it also be interesting, maybe as future work, to do the opposite? So try to explore how the Web of Things features that, say, a CoAP OSCORE system provides today can be implemented in a pure NDN ICN environment. I guess this is something that you partly have done before, but so this is how I would normally try to do a comparison.
Yeah, well, I mean, so we did not consider this idea, but I think it could yield some insights, at least on the difference of the protocols and how it may even emerge some new properties that we didn't maybe thought of. So we could, yeah, I mean, definitely also add this to the list of next steps. Yeah,
you are still PhD students, right?
Yeah,
more work to do for your thesis, more interesting work for your thesis.
That's true, yeah.
Yeah, make it a ACM dissertation award. How about that?
Yeah, eventually.
Yeah. Any other comments people want to bring up? So, Dave or Ran, you want to just speak out?
Well, I think this question of, I think there's three things going on simultaneously here. Can people hear me?
Yeah.
Yeah.
Okay. I think there are three things going on simultaneously here. One is that CoAP accepted a number of constraints involving backward compatibility with what people have done on the web. So if you can salvage much of the application designs that were done prior to CoAP, that's an argument for living with the additional complexity of something like CoAP, because it leverages so much installed base and incidentally knowledge that's been built up over years. I put a comment in the in the chat, which I also think is worth thinking about, which is that at one level, more complexity, in fact, leads to more problems. It's a bigger attack surface. It's a more complex system to evaluate. But the counter to that is that if there's more modularity, because you're combining a number of smaller pieces, you can in fact argue that this can lead to a more robust system because the individual pieces are smaller and can be independently verified. I don't think this tension's ever going to really get resolved, right? So, there's two sides to this trade-off, and I think we'll be talking about the same trade-offs 50 years from now. Thanks.
So I think the Dirk typing another question here, saying that given that IoT is still under development, why we use CoAP in the first place and not directly go this data-centric direction in building the new IoT systems? This is not like the internet infrastructure where a huge existing system is already there. Any changes is anything but not immediately feasible. But when one trying to build out the IoT systems, one, this doesn't involve any other parts. Two, it kind of seems to be within the reach. I thought that's a good question. There's 9 replies. I haven't caught up with all the replies, but people can read there and join the discussion. If no further comments, I think we're done for this session. And I'd like to thank all the speakers for their great work, and also for the discussions. I think we have very good discussion. I hope that's useful to both the presenters and also the audience.